Hi everyone. So today we're going to talk about Kepler's laws. Some brief history. Until the mid-1500s, people believed the sun orbited the Earth in a perfect circle. The problem with this is that it started to not match some celestial observations. So they mapped out planetary orbits by observing the stars and their relationships to each other, and they saw that this wasn't making sense, the idea that the sun orbited the Earth. Back even earlier in the 2nd century, Claudius Ptolemy, he developed the idea of epicycles, right? And this is the idea that planets, not planes, planets, excuse that typo, they travel in small circles while simultaneously traveling in that large orbit. So they're doing little mini circles while traveling in a large circle. This better matched data, but not exactly. In the mid-1500s, Nicholas Copernicus, he developed the idea that the Earth and other planets orbit the sun in perfect circles, right? So this bit data even better, that the fact that planets orbit the sun, but it still didn't match data exactly until Kepler came along and reconciled data with theory. I just wanted to note that the following definitions that describe Kepler's laws, they apply to just, the way I state them only applies to our solar system. So when I talk about the object orbiting, that I'm talking about a planet orbiting, and the object being orbited is the sun. So planets orbiting the sun in our solar system. In actuality, Kepler's laws, they apply to all star systems in orbit, and not even just that. They can even apply even more generally just to having one object orbit another object. Right? So, for example, these laws apply to a moon orbiting a planet. Alright, Kepler's first law of planetary motion. This is known as the law of ellipses. Basically, each planet travels in an elliptical orbit around the sun, and the sun is at a focal point of this ellipse. So if you don't know what an ellipse is, it's a shape, two-dimensional shape. Take a circle, squish it a bit, you get an ellipse. It's this shape here at the bottom. The object being orbited, in this case the sun, it's at one of the foci of the ellipse. And the planets, they travel in ellipses around whatever they're orbiting. So they do not travel in circles. What was really great about this idea is that ellipses, they fit the data that they observed of the celestial bodies perfectly, right? The fact, so here theory matched data, which is awesome. Kepler's second law states that, okay, sorry, I didn't write it was also known as. Kepler's second law is also known as the law of areas. So if you analyze the planet moving around in this ellipse around the sun, if you have an imaginary line as it draws around the arc of the ellipse, if you track the time it takes to travel a certain arc and compare it to another piece of its motion, if the area this arc, or excuse me, the area this line sweeps out is the same, that means the time it takes for the planets to travel is the same, right? The same goes if you time, say, 20 days. So you time the takes, I say here, it may not be the exact example here in the picture, but say the left blue area is the time it takes for it to travel 20 days. That means if the areas are equal, that means that it takes 20 days to sweep around that right side of the path. So a corollary of this law is that planets, they travel faster when they're closer to the sun than if they're away from the sun, right? And that's because the way it has, if you analyze this this picture, you see that this has to be true in order for it to sweep with the same amount of areas in the same amount of time, right? So same time, same area. That's Kepler's second law. Kepler's third law has to do is basically this formula, the relationship between the period and the radius. So what I have here is radius, so the distance the sun is away from the planet. In this law, we're generalizing this formula to assuming it's a circular orbit. I know we just said in first law that's not the case, but mathematically this is simpler, and we'll be dealing with centripetal motion. So basically, the period, so the time it takes for it to complete one full rotation, period squared is proportional to the radius of the orbit cubed. Right? And then we have a proportionality factor here of 4 pi squared divided by g times m. Right? Just also note we can manipulate this formula to get period and tangential velocity. The tangential velocity part takes a little bit more manipulation, but if you look in your reading, you can see that derivation. It's a quick one. It's also, I believe, on the next page. We can talk about it briefly, and if you still want to know how that formula came around, you can ask me in class. Now, I just want to note that in this formula, this m, this mass in this formula, is the mass of the object being orbited. So if you have the Earth traveling in a circle around the sun, it is the mass of the sun. Right? So a lot of times when you deal with these formulas, big M is the big mass or big object. That's generally how it's known. So how do we get this formula? Right? So if you're interested in that, you're in for a treat. Alright, so when something's in orbit, we know that the centripetal force is caused by the gravitational force. Right? So remember, centripetal force is equal to mv squared over r. So if you look at this top left box, we have mv squared divided by r, and that's going to be equal to our gravitational force, right? The only force causing our circular orbit is gravity. So that is our net force. That's g m1 m2 over r squared. Here we're going to call m1 big M, right? So the mass of the object being orbited, and little m is the mass of the object doing the orbiting, where r is the distance from the center of mass of big M and little m, right? So basically the center of one object to the center of the other object, if we're dealing with something that has uniform density. Alright, set those two formulas equal. And we could also use the relation. So if you want to actually, remember on the previous slide I said we can derive a formula for the velocity. You can do that just by rearranging this formula, solving for v, and you can get the speed. When it comes to getting the relationship with period, we can plug in the fact that we know that our tangential velocity is going to be, remember, this distance over time. If we consider just one period, so run one circle, one circular path, that's our period. We travel, the satellite is traveling 2 pi r. Remember, satellite just means an object that is orbiting another object, right? That's what a satellite is. So anyway, so our satellite has a velocity of 2 pi r over t. So we plug that into our left-hand equation, and that becomes this big box here on the left-hand side in the middle. I'm just plugging in our expression for velocity. You can rearrange this, solving for, well, they solve for something else, but you can just rearrange this and simplify, and you get this relationship here in the bold on the right. T squared divided by r cubed is equal to 4 pi squared divided by g times big M. One thing to note is that the mass of the satellite, or the object doing the orbiting, cancels out. It does not matter what the mass of the object is. So the planet orbiting the sun, doesn't matter what the mass of the planet is. All that matters is the mass of the sun, right? And what's important about this is just basically the relationship that your period squared is proportional to the distance between the objects cubed. Right? So the square of the orbital period of the planet is directly proportional to the cube of the semi-major axis of its orbit. So semi-major axis just means the distance between them in this case. What does this mean, proportional? This is actually what this, or excuse me, directly proportional. That's what this graph here to the right shows you. Oh, the axis is slightly cut off. I'm sorry about that. But on the y-axis here, we've got the distance between the planets. So this is our solar system. So this is the distance between the center of the sun and the center of whatever planet we're plotting here on this line. And our x-axis is the square of the orbital period in units of years. Right? So period squared. Just to mention, the y-axis, you might be asking what's AU cubed. AU is an astronomical unit. It basically is a unit used in space that's really big. So because stars are far away from each other, basically, long story short. Doesn't really matter. But what you'll see is that this relationship is linear, right? You can actually see that the planets, when you plot them here, the relationship between their orbital period squared and the distance the way they are from the sun cubed is a linear function, and that's what it means for it to be directly proportional. Right? So I also forgot to mention that this third law is also known as the law of periods. Oops. Anyway, if any questions, just see me in class. Bye.